start and resume recording. And Mr. Barlow, there is an audience waiting to hear about the NVMe strategy, so hit it.
Fantastic. Good day, everyone. My name is Rich Barlow. We're going to talk about our NVMe storage strategy update today. So let's be really clear first about our session goals. There's three things we're trying to do here. Number one is understand our NVMe, NVMe-OF, and SCM strategy. Now, I haven't defined those terms yet, and I will on the next slide, but we're hoping when you walk out of here, you can have a good sense of what our plans are for these technologies. Number two, we need you to understand NVMe and SCM technology enough to have a customer conversation. And, how many of your folks are asking you about NVMe today? And I'm expecting some hands to raise, something to that effect. That's great. We're hoping after this session you'll have the ability to further those conversations and have them more intelligently, right? How many of your customers are asking about storage class memory or next generation storage media? And we'll see if anybody raised their hands. I'll say, it's surprising. We don't see a whole lot of questions about this yet, but as you're going to see in this deck over the next 5 to 7 years, there's going to be a lot of transitions coming that are going to be very interesting to what we do here at Dell EMC. And the third thing we're going to do is learn to compete against the NVMe threats in the marketplace. Specifically, we're going to talk about NetApp, and we're going to talk about Pure and what their NVMe strategy is, what they're doing with NVMe, for one. And two, what do we say about that? What's our response to that? Okay, so hopefully at the end, we're going to come back to these goals in the end, and hopefully we're all going to agree that we've met these three goals. If not, let me know. Now let's look at some storage technology transitions. So one of the important things you understand is this NVMe and storage class memory transition is not new to us. As a company, Dell EMC has done many transitions. Let's look at the first one. We have a media interface transition. A media interface is the way that a drive talks to a controller. That can be the drive inside of a server or the drive inside of a storage array. So this is literally how it talks to the drive. So let's look at this. How many of you folks remember parallel SCSI? And wait for people to raise their hands. Or parallel ATA. If you looked in an older computer and you see that big blocky black connector on the back, that's a parallel ATA interface, right? We had fiber channel interfaces. Those are deprecated a couple years now. Almost every system we sell now is a SAS and a SATA interface. So what we're going to talk about is a new media interface called NVMe today. We've also had media transitions. In the past, we had old spinning drives, did spin and drive stuff, and we're going to talk a lot about that today. That I think will be interesting to put the whole spinning drive and flash thing in context, right? The next thing is NAND flash. We have flash drives now. We have single layer, multi-layer, triple layer, quad layer, lots of different kinds of flash technologies. And so what does NAND mean? Let me ask the question to the crowd. What does NAND mean? And hopefully somebody will respond. It means not and or, which is a logic gate type, which is what we've named it after because flash drives tend to operate a lot like a logic gate. What we're seeing in the future, though, is something called storage class memory, an example of which is Optane. How many of you folks have heard of 3D Crosspoint? Right? People raise their hands or not raise their hands. Great. What have you heard about it? Hopefully some people shout some stuff. The next interface we're looking at, or transition we're looking at, is our host block interface. A host block interface is how a remote server gets a block device, or a LUN, off of a storage array, or off a remote array, right? Back in the day it was parallel SCSI. Remember the big fat white cables the size of quarters all over the place? Today we're using fiber channel and iSCSI, and it's important to understand why. So fiber channel uses its own special wires, whereas iSCSI is over IP, and we'll talk about that. It matters. That's something in our future. We have the same distinction going on in the future. But the transition we're looking at is we're transferring to NVMe-OF and RDMA. So we've done this before. No surprises here. So just to get some words out there, things we're going to discuss today, we're going to talk about non-volatile memory. This is things that have no moving parts that persistently store data. Examples would be flash and or NAND devices. There's a new subset of flash NAND coming called storage class memory. It's much faster than we think of a flash drive. In fact, as we'll see, some of this stuff is faster than DRAM inside of a server, incredibly fast, right? We have NVMe, or non-volatile memory express. We're going to talk a lot about this. This is an interface to connect your drives to a PCIe bus inside of a system. It's inherently local in scope. In other words, NVMe is inside of a storage controller to its disks. or inside of a server to its disk. It's not across a fabric like Fibre Channel. If we want to do that, we use something called NVMe OF, or NVMe over Fabrics. This is how I get NVMe out to a remote server via Fibre Channel, or InfiniBand, or RDMA over Ethernet. So, something to understand is that we have a position of leadership in this market. In 2007, we were a founding member of the NVMe HCI working group, and we were the first infrastructure vendor to be involved with this back in 2007 to help develop the standards for this. Those standards are very important. You'll find that sometimes our competitors don't follow those standards, and they usually end up regretting it. In 2011, we were a founding member of the NVMe Promoters Group, which helped publish the first NVMe spec in 2011. In 2016, we released the first all NVMe shared array. How many folks remember DSSD? We'll probably have 25% of the people in the room raise their hand, because a lot of people are new. DSSD in its day was by far the fastest storage array on the market. It's no longer on the market. We're taking that technology and put it in other places. But here in 2018, we have an entire portfolio of NVMe offerings. We have servers, we have storage, data protection, all sorts of NVMe technology. But let me ask you folks a question. Where's the first place that Dell EMC used NVMe? And I'll let the clock tick. Doot, 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 doot. And the answer is, the first place we use it was in the vault drives of a Symmetrix. About 6 months after that, we started using in our PowerEdge servers. So we've been using NVMe in our systems for a very long time. NVMe is nothing new to us. So we're working very closely with our suppliers, and we're going to be a leader in the NVMe field. Before we talk about NVMe itself, it's important to understand why we're talking about NVMe, right? There's a reason that NVMe is important, but that's not NVMe. And let's look at that. So I have a graph here. We have latency as our horizontal graph and cost as our vertical graph. Now we say cost in the near term because if you go 5 to 7 years out, this graph starts to flip up a little bit. But in the short term, let's look at this. So we have hard drives, right? HDDs, hard disk drives. These are, spinning drives. Notice we have a SATA attachment, that's an attachment protocol, and we have a SAS attachment protocol. Notice that we get a little better performance by changing out the actual protocol we use to connect to it. Same drive, different protocol, a little bit of difference. Today, most of our storage arrays are flash-based with SAS connectivity. In other words, we're using SAS to connect those disks to the back-end controller. On the market now, for the most part, are those same flash drives connected with NVMe, right? So that gives us a little better performance with the same media. But the real thing that's really exciting to us is this. With storage class memory, we get tremendous performance, right? But it requires NVMe to unlock that performance. As we like to say, that's no moon in our Star Wars theme here. That's like the Death Star of storage, and we'll see why later. Some of the graphs we have for this are unbelievable, interesting stuff. So, before we get into the devices, let's talk about latency in human terms. Let's put this together in a way that we can understand this latency thing we're talking about here, right? So we have CPUs, and within the CPU, there's something called SRAM, layer 1, 2, and 3 SRAM. If I need more memory, I connect up to my direct memory interface out to DRAM. That's the actual RAM inside of a server. If I need more storage past that, or persistent storage, I can connect out to flash inside the server via the PCIe bus. If I need even more, I can connect across a fabric to an all-flash array. Now let's give some numbers to this. There's some sizes. Let's give some latency numbers. So it takes about 1 nanosecond to connect from a CPU register to SRAM, about 10 nanoseconds to go to DRAM, about 50 microseconds to get out to server flash, and about 500 microseconds to get out to an all-flash array. Let's put it all in the same terms we understand it, right? So let's put this in some human understandable terms. I'm standing in front of you right now so you can see my hands, right? In 1 nanosecond, light moves about 1 foot, or 0.98 feet in 1 nanosecond, right? So in the time it takes for a CPU register to grab something out of its local memory, light has moved 1 foot. That should boggle your mind. You should sit back and go, I cannot believe that humanity can build things that fast, right? But we can. So in time to get to something out of DRAM, light can go about 10 feet. That's about the width of the stage right here, right? So the time it takes for standard using SAS bus going out to get something from a local flash drive is 50,000 nanoseconds. And the amount of time light can go about 10 miles. So it can get to about to the city limits of Las Vegas, and we're standing at the Mirage right now. So we've gone from 10 feet to 10 miles, which is an amazing increase in latency. There's a huge gap here, right? Now to get to an all-flash array, light can go from here all the way to Death Valley. That's the amount of time it goes. Now, if I put a spinning disk drive in there, which is about 12 million nanoseconds response time, light can go all to my house from here to Richmond, Virginia, is about the delay. So what I'm showing here is that there's a huge gap between the memory inside of a system and any other kind of storage. We're trying to fill that gap with storage class memory and actually make it better. There's actually things we're looking at that are faster than 10 nanoseconds. What if we do something here? That's what we're talking about. Let's look at the devices themselves. So on the vertical axis, I have size. The horizontal axis is latency time. Understand these are powers of 10. So going from DRAM, that's in nanoseconds. Each one of the marks is 10 times more latency. So this is not, don't think about this as being a flat graph. This graph is actually almost exponential in time, right? So SAS hard drives are all on the side. Notice a huge gap in the middle there. There's an opportunity here. The first thing we're going to be looking at, the first thing that's going to come to market through us, is NVMe connected storage class memory in SSDs. Let's unpack that. It's going to be connected to the bus to the system via NVMe, right? And we'll talk about what that means in a minute. But it's going to be storage class memory. It's going to be far faster. Look at the latency times for our NAND flash. This is at least 10 times faster, maybe actually 50 to 100 times faster. But it's packaged like a drive, right? They go out in a remote drive. The next thing we're looking at that's coming out, and this is in the not near future, but fairly near future, is NVMe SCM in DIMMs. In other words, this stuff plugs in like memory, and it's accessed like memory. It's incredibly fast. And this is what I'm excited for. Notice we have an NVMe storage class memory. It's in DIMM. It's actually faster than DRAM. And that's in the horizon. We see it out there. So what we're doing is we're looking at storage technology called storage class memory that's far faster than anything we have today. It's far faster than any kind of persistent storage we have. It's going to help fill in this gap and give us new opportunities. So what does this enable? Incredible large in-memory data sets. So because this stuff's all persistent, right? Because it's persistent, I can load huge data sets into memory. And then if I reboot the system, I don't lose that data set. Okay? So I get things like fast recovery times, really fast write commits. Think about NVRAM for this, right? New workloads. There's a lot of things to do with this that we haven't even discovered yet. We haven't even found these things yet we're going to do with it. So that's what we're going to be connecting to it. Let's look at how we're going to connect. Let's look at this NVMe thing. So what is it? What is non-volatile memory express? It's a specification for SSD access to the PCI bus inside of a machine. It was designed originally for NAND flash media. It is based on standards developed by the NVMe working group. What makes it so amazingly different and new is we have a new modern command set, which we'll talk about, and we have very high parallelism and very deep queues. And we'll talk about those two things. But the thing I want you to understand at this point right now is that NVMe is for local PCIe storage access. What does that mean? I'll look out at the crowd. What does it mean to say it's local access? Well, it's local to that system. In other words, if I had a server with NVMe drives, the drives in that server could use NVMe to connect into the server. If I had a storage controller that was NVMe, a shelf of disks could connect to the controller using NVMe. But it's for local PCIe storage access. Let's look at the first reason this is so amazingly fast. The first reason is we have a new command set. Let's look at how SCSI and SAS work. So SCSI and SAS were both developed back in the day of spinning disks, back when hard drives had platters and arms and actuator arms and servos and all kind of cool stuff like that. So it's designed to deal with that kind of stuff. Back when hard drives first came out and SCSI and the SAS command sets came out, hard drive controllers were fairly expensive. So what they did is they mounted the drive controller actually inside the server or the storage controller itself. The drives themselves are very dumb. The problem is they had to do a lot of stuff. If I'm getting something off of a spinning drive, I have to use the right sector. I got to spin to the right track. I got to pull the right block out. I have to know which tracks are faster than other tracks. All kind of things that have to happen here. The storage controller itself had to know all those things. And in order to communicate all of that, the command set was very complex and is a massive overhead for modern devices. So modern devices aren't like that. For example, how do we do garbage collection in Extreme I/O, crowd? And hopefully somebody says, well, we don't. Right, because how do we do garbage collection in Extreme I/O? Well, the disks do their own garbage collection. Fantastic, you got it right. Why? It's because the new drives themselves are smart. They don't need to be told every little thing they need to do. They need to be asked to retrieve data and store data, and that's about it. So because of that, the NVMe command set is very, very, very simple. And because of that, it's very lean and very fast, which gives us a 20 to 40% CPU saving for the same operations. This is incredibly important. If you're not in a scale-out world, in other words, you're not on a Power Max and you're in a system that is non-scale-out, saving CPU becomes very important to you because you're limited to the CPUs inside that system. So this streamlined command set is very important. Next, we have a high degree of parallelism in queue depth. Now, we have an activity here, and I'm going to describe the activity to you folks on the phone. I'm going to describe the activity, I'm going to walk through this, and I'm going to stop and get some comments, okay? So let's look at the first thing. Let's look at a traditional spinning hard drive on a SCSI or a SAS bus. What we're going to do is I'm actually going to pass out balls to people in the first probably 10 rows, right? And we're going to pretend like these balls are in a hard drive. What that means is when I need a ball, a specific ball, I have to have the ball passed to the front of the row, and then I get the balls one at a time. So I'd walk to the front row and say, okay, fourth person back, pass up your ball, and they pass it up, and I take the ball. Then I walk over to another row and say, okay, fifth person back, pass me your ball, and they have to pass it up, and I get the ball. The important thing is I have seek time. The drive has to spin to a specific track, and I only get one person at a time, one command at a time being executed. Because with a spinning drive, it can only give you one piece of data at a time because there's only one read-write head. Now today, we're connecting flash drives to that same technology. Well, the problem is with flash, all blocks on the whole thing are available at the same time. Right? Flash isn't a sequential media like that. Flash is really random and parallel. But with SCSI and SAS, I still have one arm, so it's faster. I don't have to wait for I don't have to wait for the queues to come to me or anything. I don't have to wait for the conveyor belts. But I still only get one picking arm. So to do that, I'm gonna point to a person and say, "Hey, you fifth row, third person, throw your ball at me." Okay, now you eighth row, fifth person, throw your ball at me, and it's much faster. Now, if we take a flash drive and connect it with NVMe, all of a sudden it's a different world. I've got that media where all the blocks are available, the same seek time and latency, but I've got 65,000 arms. In other words, it can, in parallel, execute 65,000 operations. And every single one of those arms has a queue behind it for 65,000 more operations. What this gives me is a world where every CPU core could have its own queues and have its own pieces. And applications can have their own queues. There's a tremendous amount of ability to run parallel operations. Now, to demonstrate this, I want everybody with a ball to all throw them at me at the same time. And the person in the front gets pelted with balls. Okay? Let's stop for a minute. Stephen, questions, comments, concerns so far? Because this will be the first activity.
All right. Anyone with questions or comments on the slide so far?
I took some notes. Do you just want me to send them to you, or want me to...
Yeah, if there's anything you feel needs discussion, let's bring it up. Otherwise, you can post in the chat. You can just quickly name off a couple of things for emphasis.
Yeah. So slide 2. Just do a Control F on the deck at some point and do NVMe-OF and then NVMe-OF without the dash. We use it on slide 2 with the hyphen, which I think is the correct way that the working committee uses it. And then in the very next slide, slide 3, it's omitted, right?
Got it.
And then also under that same spirit, slide 6, it's a title separator. It says NVM/SCM overview, and then slide 7 says NVMe.
I see what you're saying. No, you're right. You're right. Let's do this, because technically that would be correct.
When you were speaking to the audience, you asked when was the first time we used NVMe, and you said Symmetrics. And though VMAX 3 is of the Symmetrics lineage, I believe the 40K was the first time we totally removed it from the badging and the logo. I just didn't want anyone to think we're using it back in the Sim 6 or Sim 5 days, which was the last real, true, only Symmetrics by that name. You know what I mean?
So I should say VMAX rather than Symmetrics, right? Just say
VMAX 3. I would say VMAX 3.
Okay. I'll put that in the notes.
Slide 8, I was real happy to see that. I've seen that before, but it used to be normalized to time, and I believe that we made 1 nanosecond a minute, and then by the time you get out to the last it's in days now or whatever. I think that on the bottom of that slide we see capacity, and then we see time, and now we're extrapolating out to something they know, but we've changed the KPI to distance.
That's right.
You know what I mean? So
I think hang on. Let me. I'm gonna pull the slide because I think I know what slide you're talking. That's where I stole this from. This is new, so we haven't discussed this yet.
No, I've seen it before years ago, and I was thinking as we were going through this last time, boy, that'd be the perfect thing. It used to be normalized in time. Like,
yep.
I have it somewhere. I believe Chad had it in his slide.
Yeah,
it's right on screen.
I sent it to you. So
yeah. There you go.
My opinion is it helps me understand when you were going through that slide. I was really confused about like this kind of trying to conceptualize the speed of light and this distance to Death Valley that think I'm near because I'm sitting in Vegas, and maybe I tend to maybe agree with the comment that leave it in, but maybe it's a different measurement that we can relate to a little better. I don't know.
Well, no, and this is a question. Once again, we haven't discussed the slide yet, so I want to discuss it now, right? I thought that the distance was more what's the right word? More relatable, because I can actually stand up and hold my hands a foot apart. And then the stage is about 10 feet wide. In every place I've ever been, there's a stage about 10 feet wide. I thought that this gap here was very visually stunning, from 10 feet to 10 miles. Right?
I think it works. I think the way you change it, Rich, to make it work is you were talking about the speed of light, and nobody can measure the difference between the speed of light and 1 foot and 94 miles. It's all the same. I think if you said to him, it's the difference it takes for me to walk 1 foot, to walk 10 feet, to walk 9.7 miles, to walk 94 miles, and you're good to go.
Huh. That works too. Does that? And I think that's actually very visually, mentally clear.
I like it, Rich. Just remove the speed of light stuff.
Got it.
I was. You were saying it, and I'm like, I couldn't grasp it in my head. Although I understood, you know what I mean?
Let's do it this way. How long?
It might also make it a little easier to digest if you said about 10 miles and about 100 miles, right?
Agreed. Yeah, 1, 10, 10, 100. I like it. Yeah, I like it.
So we could, because it technically, this is pretty correct. Just do this.
Yep.
Yeah, it tries to point home that it's latency, right? That's what we're trying to do.
No, I got it, and I like that. Yeah, I thought that the time, it's all on different scales is the problem. I get from seconds to weeks to months, and it's hard to visualize all the scales in my mind for that. But I like it. Thank you. You guys like where that slide is, though? We talk about the new stuff that's coming. Then we talk, what does latency mean? Right? What does that mean? And this one would be equivalent, when I do the spinning drive, it's equivalent to walking to my house in Richmond. That'll be fun. From there, we go into the actual hierarchy with the gap. The gap is what we're outlining here.
Yeah, I think it works where it is.
Okay.
Is 7 and 9 similar, or could that be set on one slide?
It can be. There's two different things I'm trying to say though. Is I'm trying to say here that notice we have two. Oops, didn't mean to move that. Notice we have a media, the same media, but an interface transition. We get a little benefit here. Here today we have the same media and interface transition. We have a little benefit. The real benefit is the new media. That's the point.
I see.
This slide is about honestly, the slide's more about the gap. The fact that we have this large gap right here today, and that we have products coming to fill that gap.
Okay. The Death Star, many times when you go somewhere, it looks great on your screen and whatnot, and you get to one of these projectors and white on a light gray might not, and it might not be able to see NVMe that well. So.
Okay.
That's the other thing
What do you guys think about that at all? I was hesitant to put it in because it kind of, I mean, it's funny.
Yeah, but the Death Star blew up and everyone died, so I don't know.
Awesome.
Yeah.
Rich, I'm gonna totally expose myself. I didn't get the reference because I just.
Yeah, I was having it. It was really, you're really stretching it there, Rich. I don't know if I got it either.
I just, come on, man. They come out of hyperspace and there's an asteroid field and they think
Well,
that's
put the Millennium Falcon there then.
You're no
Yeah.
fun.
Yeah, put the Millennium Falcon in there. Change all the miles to parsecs in the previous slide or something. I don't know.
Speaking of that, and this may be me, I'm one of these guys, I have ADD, I'm sitting there trying to read an article and there's something, clickbait flashing up. On that first slide where you start out with the topics that we covered, that Death Star heads up thing is like, because you're trying, whenever you have words, right, you're either reading them or listening to the presenter. Well, now I'm looking at a third thing, which is the Death Star's radar, or the whatever that thing is. Yeah.
They're in the trench, man.
That's the X-wing fighters, locking in on the exhaust port.
Yeah, I mean, it's fine looking at it here, but when you're playing it, it's animated, and it's very visually distracting.
I don't know. I kind of like it, but that's just me.
I tell you what, let's I think maybe we run it once and see and ask afterwards, because honestly, just this may not display very well on the big screen anyway, because a lot of times the reds don't come through at all.
Well, I guess what's the point of it as far as learning NVMe?
It's supposed to be staying on. You remember, stay on target, red leader, stay on target. It's that kind of thing. Yes, I'm a Star Wars fan. What are you gonna do, right?
Right.
So what else in terms of content here do you guys see? Do you think that we got the point through about NVMe, what it is, why it's awesome?
Yeah, I think it was great, actually. Other than those little things I pointed out, it's fine.
This is going to be fun.
I think you make the latent point well, and I think you also make the queuing point very well, right? And even though flash drives on SAS don't have the same queuing problems of the hard drives, there still is only one damn queue.
Yep.
The other thing is in the PowerMax world, right, we're actively using both ports. You have multiple queues on multiple ports, whereas even though the flash drives have two SAS ports,
yep,
because of the way the controllers work, we can only really use one at a time.
That's right. We can use
They're active, and we can fail over to the other one.
That's right.
But because of the queuing stuff, you can't drive I/O down both sides at once.
That's right. And it is amazing what NVMe does.
Yeah.
Go ahead.
I've got a quick question. What's the target audience here? And the reason I ask is, when you're talking very quickly about certain things, do you think the target audience is going to understand what you're talking about? As far as persistent drives and stuff like that, is this for an SE community or?
Yes.
Yep.
Yes, it's SEs, and I think they'll all understand everything so far. Would be my vote.
If
Okay.
they don't, we need to take them back to school.
And then my only other comment would be, maybe at a high level, one of the things that somebody told me once was that, what NVMe accomplishes is it decreases the amount of chatter during an I/O process. And maybe that's at a high level, and then you drop down. This would just be perhaps a recommendation, where you drop down and say, let me tell you what I mean by that. And then you go into a little bit more detail. Because then at worst case, at the highest level, they understand that this is an advancement in the protocol that decreases the amount of chatter every time you do an I/O, for example. That's the thought.
I mean, I think we talked about that directly under the command set.
Make that point.
Yeah, that's the command set.
Okay.
I mean,
We
that's
used to have a slide.
And we're the only reason we're mentioning the command set, because that's really not the advantage. The command set really isn't the big deal. It's really the parallelism that's the big deal. We're mentioning the command set because in the competitive view later, that becomes important.
At one point we had a slide in the deck because I know we had some dialogue around it. But when I heard the NVMe committee present it, I think they said, the SCSI command set is over 700 commands, and whereas NVMe is, I don't know, 60 or something. But
yep,
it was pretty compelling.
In the talk track that we can talk about that there's there's hundreds of commands on the SCSI set, and on the NVMe there's like 13 essential commands. Let me keep going, guys, because some of the questions you guys asked might be actually done in the because we didn't finish this section. Let me finish this section out.
Please go on mute, because I assume, Steven, you're going to start recording again?
Yeah, I've been recording the discussion as well.
Okay, cool.
Okay.
So, after everybody throws the balls at me, we pick all the balls up, which is going to be great. That's fantastic idea, Kurt. I really appreciate you getting the balls together, man. I'll say up front that, I really appreciate that, brother. All right, so let's put it all together. Let's look at these things together. So let's look at latency. We have a spinning hard drive connected to a SAS drive. We have a flash drive connected to SAS. We have a flash drive connected to NVMe, and we have this new media plus NVMe. So when we went from hard drives to flash drives, we cut our latency by 2 orders of magnitude. It's 100 times. If we were displaying this on a big screen right now, this latency, if it were actually to scale, would be through the roof of the room. It would be so large, right? It might be through the roof of the building, all the way down to this. Tremendous decrease in latency. So what NVMe does, it drives down the connection latency. It removes this orange portion here, which is significant. But the big bang, and that's what we're doing in the market today. That's what all of our competitors are doing. That's what we're looking at right now is back-end NVMe, getting that connection latency pulled out. What storage class memory is going to do is give us a 10 times reduction in latency on what we already have. So a tremendous change. So let's look at a graph. This is something Intel did for us, which I think is really interesting. And look at this graph here. So we have a normal SAS-connected NAND device, right? So response times, this is in microseconds. Keep in mind, this is a half a millisecond, right? And this is important. We try to make it, if we make this in milliseconds, this graph starts looking really weird. So when we had half a millisecond, we're about maybe, what do you think, guys, about 120 megabytes per second of throughput. We take the same drive now and connect it with NVMe. Now I'm getting almost twice. Look at this. I'm getting maybe 275 megabytes per second at half a millisecond response time. Now let's look at a SCM device connected with the same protocol. That's mind-boggling. By the way, this little line right here goes over to about 2,500 before it starts to knee up. That's what we're seeing, is about probably 2,500 megabytes per second at this latency. Which, what do you folks think? Is it maybe 10 microseconds here, maybe 15 microseconds? That's what storage class memory is going to bring us. We need NVMe to get there. NVMe is needed to get there. So, next let's look at NVMe over fabrics. So we've got this crazy fast system. We got all these queues, all this neat stuff inside of a controller. How in the world do I share it with my hosts? Because, we're a storage company, and we sell storage arrays. One of the things we sell, at least. So, our friends at Brocade, they posted this, and we think it's true and very interesting, actually. And hopefully there's some Brocade people in the room who will nod their heads at this. There are 3 phases to NVMe adoption we're seeing in the market. The first phase is you put NVMe in your servers, and we've been doing this for a while. PowerEdge started using NVMe in 2014. And basically they're SSDs that go inside your servers, right? We're doing this in our hyperconverged systems as well, right? So you put them in the servers, the first place they go. The second phase is we use NVMe for storage backends, right? So we connect NVMe storage devices inside of a storage controller, but then they're shared over the SAN fabric using traditional storage methods, using Fibre Channel or iSCSI, right? Keep in mind that Fibre Channel and iSCSI are designed to move SCSI commands around, so all that single queue, all that stuff comes into play with this, right? Now, what we're looking at now, though, is NVMe over Fabric. How do I take all that coolness of multiple queues and multiple arms and reduce command set, all that kind of stuff, and actually just give it over a fabric? So what it gives me is all the benefits of NVMe over a fabric. So what I'm doing is taking that NVMe stuff and encapsulating it, sending it across Fibre Channel or sending it across IP. What it does is it lets that same parallelism and high queue count extend to remote hosts. Now, there's something we're going to look at. There's two different versions of this, and we'll talk about this. One version gives me remote direct memory access, which is a more efficient way to transfer data that bypasses the remote CPU. This is important. The other important thing to remember is there's no agreed industry standard for NVMe OF yet. In other words, this is the VHS versus Betamax time of this. There's no industry agreement as to what the transport protocol is going to be. So let's look at what Dell EMC is going to do. NVMe FC is our first step. Let me ask you folks a question. How many of your customers have a Fibre Channel fabric? And pretty much 90% of the people will raise their hands. Right. How much money do you think they have invested in that? Do you think they'd be willing to rip it all out tomorrow for Ethernet? I think probably not. So the first place we are starting as a company is with NVMe over Fibre Channel. You can transport those NVMe commands over standard Fibre Channel connections. So what it does is it doesn't give you this remote direct memory access, which is going to give me more efficient CPU utilization, but I can still use all of the NVMe constructs. And as far as efficiency, it's just as efficient as Fibre Channel is, right? Which is not ultimately efficient, but it's fairly efficient. But in the longer term, we're looking at how do we move this over Ethernet? And let me ask you folks a question. Why do we want to move this over Ethernet? And look at the crowd. Why do you think that Ethernet's important to us in the future? Well, because we see the actual throughput and bandwidth available in Ethernet networks eclipsing Fibre Channel networks. You can get 32 gig Fibre Channel now. I can also get 100 gig Ethernet. 250 is on the horizon. Terabits not too far out there. There's a lot of activity going on in the Ethernet world. Plus, Ethernet lets me do something called RDMA, which is really important. RDMA, in a nutshell, will reduce your CPU utilization even further. That's incredibly important if you're moving tremendous amounts of data, because even if I've reduced the CPU utilization by using NVMe itself, it's still going to take a lot of CPU to move a lot of data, right? This reduces it even further. Now, there's three protocols. The first one's Rocky. It's RDMA over Converged Ethernet. Problems with it, though, it requires lossless lossless networks, something called DCE for best operation, supported specifically by Mellanox and Emulex, and there's not a lot of native OS support. Next one's iWarp. The problem with iWarp is it's pretty complicated. There's a lot of hardware and software requirements for it, plus it's limited to 10 gig, plus it's supported by Chelsea and Intel, and once again, there's not a lot of native OS support. Third, we have NVMe over TCP, which uses standard switches and a very simple TCP/IP stack. It's just not ready for customer use yet, and we're looking at this protocol for long term because we think it's interesting because it doesn't require any special hardware. What you need to see on this slide that's really important is that the industry is very fragmented at this point over how this stuff's going to be delivered, and because of that, we're going to add more of these to our systems as the industry ecosystem maturity develops. We're not doing this until we know which way the industry is going to go. We have some. I think we learned a lot with DSSD to be careful and not jump out here too far and too fast. So let's put it all together. So back in the day, you had a storage array, with spinning drives in it, 7,200 RPM drives, and almost all the latency. This is response time here. This graph is response time. Almost all of the latency of the entire system was in the actual spinning drives. Notice that this stuff barely even shows on the graph anymore because my response time is so high for the spinning drive. It's 1,000 times slower than your back-end connections. So I'd say I'm disk bound, right? Then SSDs came out, and they gave me a 2 order of magnitude or 100-time reduction in latency. Now I draw this graph again, and I have to rescale it. Notice over here, I'm in sub-millisecond times. When I rescale it, all of a sudden my storage controller becomes my bottleneck here. It's 6 times slower than my back-end connection. So guess what? We say we're array bound. Now, as of storage vendors, we found ways around this. That might be one way with a VMAX. That's a great one. So let's say we replace this with VMAX. I have scale out back end. So I have multiple. I'm not worried about being CPU bound at my controller level. I have NVMe on the back end. All that sort of stuff that drives down the latency for my storage controller. Now all of a sudden, my host is actually my latency, is my bottleneck. Bottlenecks always exist. They just move around. What we're doing with NVMe is we're moving that bottleneck somewhere else. We're taking out the back-end connect and front-end connect bottlenecks. Let's look at this. Let's look at a way that NVMe can help us here. Let's do a performance calculation. I have an application or a group of apps or a cluster of VMs or something that requires 5.6 megabytes per second of throughput. A lot of throughput here. Okay? So put it on a graph. Now, in order to get that to that particular host, I need 4 fiber channel connections. Just doing the simple math. I need 6 PCIe buses in my storage controller, which require 10 SAS buses, or 10 SAS lanes, which I can deliver all that with 4 flash drives. But I have to add a 5th one. And why is that, folks? Because I can't connect 10 SAS controllers to four drives. They're all dual ported. So in order to get that connection, I need to add a disk. I need to add a drive. So get me 5. With NVMe on this connection here, I can eliminate that 5th drive that I need only for SAS connectivity. And also, I'm not saturating that bus. With this, I was literally using all the SAS connectivity for 10 entire SAS lanes just to support this one application. With this, I'm not. Front end too. It gives me the ability to deliver that I/O to that application through the storage controller in a much more efficient way. So let's look at what we're doing with NVMe at Dell today, Dell EMC. Now, really, I'm personally seeing 2 types of customers out there. I call them the early adopters, and their mantra is, I think NVMe is cool and I want it because I was told that I needed it. So who do you think this guy's been talking to? Now look at the crowd. And we all laugh about it, and they're like, yeah, they talked to Pure. Right. Because Pure is convinced their customers that NVMe is better than sliced bread with peanut butter on it, man. It's the thing that will save humanity from climate change. It's the thing, right? On the other hand, I have conservative customers who actually need NVMe, but they say, well, but it's only available on the high end and I can't afford it. These are treats for today, though. NVMe adoption is really not expected to reach critical mass for years. IDC is saying 2021, when more than 50% of arrays will be NVMe. So it's not really mainstream today, but it will be. Also keep in mind that our competitors only really have real NVMe in the high end of their arrays. For example, only about 15% of Pure's arrays they sell are actually NVMe. They talk about a lot of it. They don't seem to sell a lot of it because it's really expensive. We'll talk about why. And keep in mind, we do have many NVMe products today in many price bands. Did you know we have NVMe in our mid-range today? Not in the mid-range array necessarily, but in our HCI. Let's look at what we have. Because we're very confident that we have a strategy that we've been executing on, that we are proud and confident that it's the right thing to do. So today, for NVMe, we have PowerMax, and we'll talk more about PowerMax on the next slide. But PowerMax is a full NVMe backend, has scale out, all the stuff you can beat up Pure and NetApp with. Our PowerEdge servers have NVMe backends as well. Our VxRack and VxRail use NVMe connected cache drives. And why is that? Why do you think that's important? Well, because The performance of the cache, and especially for vSAN, the performance of the cache defines performance of the entire system for the most part. It's very important, which means since our PowerMax has it and our VX Rack and VX Rail have it, it means our VX blocks have NVMe. Also, our data domain 4400 is also NVMe based. So we have NVMe products today. Tomorrow, a lot of people are talking about this already, our midrange.next product, which will have NVMe, and I know there's going to be a session on that about that today while you're here over the next couple days. Why is this our strategy? Because it's smart. We went to the places we were strong and make sure we kept our leadership in those places, right? And we are working into other markets as we talk about this today. So, NVMe array today is Dell EMC PowerMax. That's our end-to-end NVMe array. It's full NVMe backend. It already has compatibility with SCM, and this is important. It's designed for industry standard SCM devices. We're not having to build our own. We have brand new NVMe drive enclosures and I/O modules for this. There's actually code for this for backend I/O services, which means all of our normal stuff, all the normal awesomeness in a PowerMax works for NVMe. So full active access, all the RAID types, full data at rest encryption. So if you need NVMe array today, you need an array, we have PowerMax. Coming soon, or coming sometime, I probably won't use the word soon in the real presentation, by the way, but coming when we get finished. I'm looking for a way to say that without sounding like a dork. Anyway, it's coming. Midrange.nest is coming. And look for a session on that. They'll discuss that in a lot more detail with you. So let's look at a competitive view. Before we get into this, the thing to understand, and this is critical, what does it mean to be a trusted advisor? And this is something that I know Dan O'Brien has talked about many times. It's listening and understanding what your customer needs, period. Here's the question you need to ask yourself about your customers. Does your customer need NVMe? It's a critical question. Because if they need NVMe, we need to find a way to give them what they need to meet their needs. Our largest NVMe competitors, though, are Pure with their FlashArray//X and NetApp with the all-flash FAS A800. These, at least for me, are the two I see the most. What other ones do you see, crowd? And we'll probably spend 5 minutes here talking about IBM and maybe mentioning Hitachi and just mentioning some other competitors. Let people know there's a lot of stuff out there. These are the two we're going to talk about, though. Now, we're talking about these for a specific reason, to arm you to combat it. This is not stuff to go negative with. We need to be very careful. We need to fight back very directly with our competitors and very directly speak to their weaknesses. But then again, we just don't go negative. Why is NVMe so important to Pure? It's very important because of their active-passive controllers. This has always been Pure's Achilles heel, right? They don't have a scale-out architecture. That means, and also they're truly active-passive. I mean, how many of you folks know how this works for a Pure array? Yeah, right. We talk about it. There's one controller that's fully active. The other controller is passive. They say that's for particular reasons. We disagree. That's why we do active-active. The problem with this is this. They have no way to scale out to get more performance. So as more and more I/O starts happening, they start getting more and more of a CPU hit. Remember on that slide where we talked about the 20 to 40% CPU savings for the same ops? That's why Pure ran to NVMe and why NVMe is so important to them. They desperately need to save CPU cycles because they don't scale out, and they have no way to scale out. Some other things to keep in mind is Pure uses proprietary NVMe drives that are not industry standard. They actually have them made for themselves. I want you to think about that. Would you buy an all-flash array that required that company to make their own custom flash drives, their own custom stuff for you? The next question you should ask yourself is when storage class memory comes out, are they going to do that too? They're going to have another assembly line making storage class memory devices when everybody else in the world's using industry standard stuff? It seems like our way is cheaper. They have no end-to-end NVMe. It's back-end only. And plus all the other shortcomings. I mean, we've done Mythbusters for Pure a million times. Their Evergreen Gold, their poor overhead, all that stuff still exists in their NVMe arrays. Let's look at this. Let's compare them. Oh, sorry. We have an old saying in the South. It says, if you put lipstick on a pig, what's the rest of the saying? It's still a pig. So let's compare a Dell EMC PowerMax to Pure Storage. PowerMax is active-active, whereas Pure is active-passive. The PowerMax gives me component fault domain. In other words, I can lose a CPU or lose a RAM stick and it still runs. On theirs, the entire controller is a fault domain, so any kind of failure will cause the entire thing to fail over. We have multi-controller scale up and out, whereas their dual controller scale up only. We can consolidate block, file, IBM, iSeries, all that sort of stuff. They're block only. We have advanced proven data services. Let's talk what that means. How long have we been doing data services through our PowerMax/VMax/Symmetrix lines? We're really good at this. We know how to do it. Not saying their stuff doesn't work, but remember, all those advanced data services they do still compete with the same CPU they're using to deliver data, right? Because they only have a single controller to do it. We use industry standard NVMe. Our stuff is, I won't say it's off the shelf, but we don't have to specially custom make our own NVMe, whereas they're proprietary. Let me ask you a question. Why did they do proprietary NVMe? Why is that? Because when they wanted to do it, they needed it desperately for a CPU. It didn't exist yet. They had to make it themselves. So once they started making it, they decided to run forward with it. And we're ready for industry standard SCM. They say they're NVMe ready, they're SCM ready, but remember, it's all proprietary. Who knows? So, oops, sorry. There's a piece. I got to fix this. The machine learning the machine learning blurb didn't pop up. I got to fix that. So, why is machine learning important for this as well? One of the things we have machine learning versus and they do not. You folks remember during the transition from spinning drives to flash drives? Remember how we crushed that transition? Why was that? We had this thing called fast tiering. We don't talk about it a whole lot anymore, to be honest with you, because with an all-flash array, who needs it, right? Let me ask you folks a question. When storage class memory first comes out, do you think we're going to sell entire arrays full of storage class memory? Probably not. We are most likely going to use it as a tier, and we're really good at it. I don't know if Pure really has any experience in doing storage tiering. They've been an all-flash array. How are they going to handle that? Where's their machine learning algorithms to understand how to keep hot and cold data separate? So NetApp. NetApp's NVMe strategy. Well, NetApp continues to bet on data on tap. Now, I was at NetApp for 8 years, and they had a serious not invented here syndrome where if it was not data on tap, it was nothing. Data on tap runs the system, man. Now, they have SolidFire and they have Ingenio now, but still, from what I see at least, the vast majority of their research goes into data on tap. Now, they do have end-to-end NVMe. They have NVMe OF. Let's recognize what they're doing here, right? It's NVMe over Fibre Channel. It's only available in one model, which is their AFF A800. But it still has all the weaknesses that NetApp has always had. Keep in mind that in NetApp, they have this clustering. They call it clustering. I'm making quotey fingers. You can't see. What those clusters mean is I have dual controllers. So I have two controllers connect to the disk, another two controllers connect to the disk that are connected with an InfiniBand back in. Every single controller is a point of management, though. You manage a NetApp system. You don't manage the system. You manage a whole bunch of single controllers, right? Also, it's not true scale-out. It's no I/O aggregation. In other words, all the I/O for a particular LUN goes through one controller. That's it. And unless using infinite volumes, which are only available for a few things in a few ways, all the I/O goes through a single controller. There's no active-active abilities. Their metro clustering technology is always active-passive. And plus all the normal problems with data on tap, very poor space utilization especially. So, for example, they take 35% right off the top for RAID, for waffle, sparing, and everything else. And we don't do that. Ours is much more efficient. Like we said, if you can put lipstick on a pig, it's still a pig. So let's compare PowerMax to the Dell All-Flash FAS. We have multi-controllers, scale up and out. Once again, they're still dual controllers, scale up only. They can talk about clustering, but if you take it apart, it's still dual controller, scale up. That's still how it works. We have the controller, the component fault domain, whereas once again, their entire controller is a fault domain. We have true active-active clustering high availability, which means that a controller, any controller can see any disks. They don't have it that way. Their controllers own their own disks. And if they fail over, the other controller has to reach across the fabric to grab them. We have global dedupe across the entire system. whereas they have these things called dedupe pools. We have an RP and RTO of 0. Whereas NetApp can have an RPO of 0. In other words, they're not going to lose any data, but their recovery time is up to 2 minutes. If a controller fails, the other controller has to let that controller fail out and then come take over the disks. And as an ex-NetApp person, this was a pain in my butt. And as a person who ran NetApp, it was truly a pain. If you have an outage, it can cause you problems. We have advanced data services. They have resource-intensive data services, which work exactly the same way in terms of, like Pure. You have the same CPUs, the same non-scale-up and scale-out controllers that have to do all the stuff they do plus serve data, whereas we can scale out. We have 2 NVMe models. Our PowerMax 2000 and 8000 are both NVMe, whereas they have 1. We're SCM ready, and we know we are. They claim they are. We don't know, right? But we can say we're already experimenting with this with SCM and our PowerMax, and we have built-in machine learning. And that's important for the exact same reason I said before with Pure. When SCM comes, the advantage is going to be to people who can use it in small amounts because it'll be economical. So NetApp, tell us about your storage tiering abilities, right? They have more than Pure does, but not what we have. Everybody claims to be the flash market leader. It's funny, if you look at NetApp stuff, they claim to be the leader. If you look at Pure, they claim to be the leader. But IDC doesn't lie. This is the actual IDC data from the last couple of quarters. And the last 4 years, you can see that we had twice the market cap of NetApp in this, right? So we are truly the leader. So let's do a quick competitive activity with what you've learned. So one day you're talking with a customer engineer at lunch, and she mentioned she'd seen a recent presentation from Pure concerning NVMe. The Pure SC stated repeatedly that NVMe is a revolution in data center storage. They also stated that Dell EMC was behind and that only an NVMe-backed system can provide the response times for applications required. Furthermore, the Pure SE stated that buying an NVMe today is future-proofing for the data center over the next 5 years. What is your 1 to 2 minute response? So what they're going to do at this point is we're going to have them talk to their neighbors, basically put together something for the neighbors. Then after probably 5 minutes of chatter, we're going to see if we can get a couple volunteers to come up and give their 1 to 2 minute response to that. What we're hoping is they hit a couple points. Number one, NVMe is not a revolution in data center storage. It's just an interface transition. This is not like the second coming of the Buddha or anything. It's literally an interface transition, which we've done a million times before. It's easy, right? The revolution is SCM, which we don't think Pure is ready for, right? They also stated we're behind. Well, behind, we have far more products that are NVMe based than Pure has. They have 1 line that's NVMe based. We have 5 separate lines of products that are NVMe based. The statement that only an NVMe-backed system provide response time for applications required. First question is, show us the performance data that the Pure SE pulled. Show us what they did to get that, to say that. Or are they just talking out of their butts? They do a lot. Last statement about future-proofing over the next 5 years is a great statement. It's absolutely true. If I had to future-proof my data center, though, wouldn't a PowerMax be a better bet? Okay, let me stop here. Questions, comments, concerns?
Hey, Rich, it's Paul.
Paul.
I love you guys. Fantastic job. I think you guys have just put together an incredible presentation here. I do. Craig and I have been chatting in the window. You can read through it, but I don't know where the 15% Pure portfolio is. Only 15% NVMe. We're just chatting. We think it's like all NVMe basically. Do you know where that stat came from?
Yeah, hang on. I pulled it out of one of our slide decks.
It might be wrong. So it used to be just the X70 was NVMe, but now they have an entire X portfolio of NVMe, and so they'll sell out of the //M and then move to an entire NVMe strategy. So we might just kind of strike that.
I believe on their earnings call somebody had asked, of all your boxes you're selling that are capable of being NVMe, how many are shipping with it? And it may have come from that. I remember hearing something. I don't know that's what it is, but
yeah, that was the statement right there. I don't know where you got it from.
So I think that would be a important point, but it's not portfolio. It's, hey, even Pure, who has an entire product line that will support NVMe, is still selling a lot of things that a lot of standard SaaS Flash instead of NVMe in those platforms, right? They're still selling a whole bunch of //M and X10 and X20s without NVMe, let alone all these things that can do NVMe. So that's maybe the striking point there. And then I want to make sure that we don't set these guys up for a battle with some of the things I think you're leaning very heavily on with Pure.
Mm-hmm.
So Pure in the field discredits our dual controller talk track against them very simplistically, and it works. So if you look at the way that our dual controllers work, like in say a Unity or historically in Clarion VNX whatever, we actually have this idea in which both controllers are actually servicing I/O, and thus we get into these conversations with our customers of you shouldn't utilize the total system or any individual, I'll say, a controller, if you will, SP, more than 70%, because in the case of the failover, then one guy has to handle 100% of the workload. Pure quickly discredits when we try and drive, hey, they have dual controllers and only one's even driving it. Like, how crazy and stupid is that? All they say to their customers is, right, we are able to kick those guys' ass with a single controller, and we're giving you a standby one for free. And they do it in the field, and it totally discredits our entire talk track about them being dual controller and the way that they architect and only have all the I/O running through one controller. So we have to be careful that we don't set these guys up to lean too heavily into that. We absolutely are differentiated in the way that we scale out and up, and we need to lean in on that. But I don't want these guys running into all their customers in their Pure battles coming back to this dual controller thing, because Pure will tell them we drive 6 nines. We have proven, I'll prove to you with stats, that we have a 6 nines available platform without scale out, and in the case of a controller failure, I can service 100% of your workload on one controller, so I'm giving you basically a full-time standby. So just be careful around how much we lean into that.
I agree. I know that Marky D is leaning into his microphone right now. So hang on, Mark. Hold the roll, man. So here's my. I don't have an argument back against that because I try to stay out of these kind of knife fights, but I know the SEs get pulled into them.
They do. Yep.
The bottom line is this: what's the highest you can drive a single Pure controller? Probably 95% utilization. Right?
Actually, you can't. And so I agree with you. So they actually have a whole bunch of problems when you drive them over about 75-80%. They start actually turning off services, and they have all sorts of problems, and we can back them into that. We don't want to get into that knife fight. We don't even want to have this conversation, is my point. Like, let's just stay very strong in the hardened points, and let's not get into these details with the guys.
Okay.
Well,
I hear what you're saying.
Hang on. Let me just weigh in here for a second.
70 is 140 is the thing.
So let me just weigh in here for a minute. I get what you're saying, Paul, and I agree with you that we shouldn't start that conversation, but we do need to play a little defense, because what Pure's been doing is putting us in the penalty box and saying you actually can't drive those controllers over 50%, because otherwise you'd be over 100% utilization if you had to fail over. We need to teach them to fix that conversation and put Pure back on their heels about that. So I agree with you. We shouldn't attack them with a single controller, but we should have that conversation around single versus dual. And listen, we should take off the table this whole idea about the fact that these controllers fail all the freaking time, because we know both of us, neither one of us fail all the time. Yeah. It's very rare that we have those kind of failures.
Yeah.
We should be weighing in more on things like, oh, I don't know, if we make a snapshot, we can mount it, and they can't. That's a much more operational and user benefit than talking and having the knife fight over whose controller fails over and who doesn't, and who has a standby and all that other garbage.
Agreed. So maybe I went into too much detail of maybe what my point was. My point was let's maybe keep the talk track crisp there. And if we have time for Q&A, especially when we go through the Pure the activity, that's I think when we can really get into some of this stuff if we need to. But as part of the flow of the deck, maybe we don't lean so much into those details. It's just my opinion, by the way. There's a lot of people on the phone, so.
Yeah, and I think that the whole thing that Rich is trying to make with this is that they don't have scale out. That's the thing we should be driving home here.
So,
Yep.
Rich, when you were talking about active passive, you put it, you drew on your experience from NetApp, and I know back from the Clarion and the VNX days, it was very apparent when this trespass thing would happen, right? So it's not so much whether or not a performance thing. I would, is it a seamless failover? I don't know, or do you start seeing timeouts while the LUNs are being mounted on the Survivor, right? You don't have those with active dual ported NVMe is the point, right?
So in the NetApp world, you literally have to set a setting in the registries of your Windows box when you do the snap drive stuff, which gives it a longer timeout. So, but you're not servicing I/O within that 2 minutes, that's for sure.
And there's no Alua you have to go mess with on a VMAX Power Mac, right?
That's right.
The concept's foreign.
Now, keep in mind, we're comparing apples and bananas, right? So NetApp and Pure, in my mind, and you have to excuse me, they're mid-range arrays because they're not scale-out, right? To me, the definition of scale-out is a definition of an enterprise array is scale-out. That's what defines it, really, in my mind. And they don't do it. NetApp, we talk about it all day. I was on the friggin' ONTAP 8 committee. It's not a scale-out array. It's scale-up all day long.
The slide that you're currently on, the AFF A800, was that from the SolidFire acquisition, its lineage?
No, it's actually ONTAP based.
Oh, okay. All right.
It's ONTAP.
Is it sellable with both? Meaning you don't have to take it with 100% end-to-end NVMe, right? Right now you can buy it with fiber channel front ends.
Yeah, you can actually, from what I understand, because I read some of the tech papers of this, I can actually do NVMe OF and fiber channel, like regular fiber channel, over the same ports, over the same physical ports.
Okay.
It's just an encapsulation, right? NVMe over fiber channel is a software piece, and this is something that I know, Kurt, you mentioned this a few times, but I should have brought it out more inside this deck. NVMe over fiber channel is literally a software change. It's just software. So
yeah, well, in fact, NetApp bills that as it's just a code upgrade to their array.
Yep.
If you've already got the box with fiber channel in the front of it, it's a code upgrade to make it available.
Right.
Part of that upgrade probably is some HBA firmware, but to the customer it does look like a software load. It's not a hardware card swap.
Right.
Well, the SAN switches in the middle would have to be the correct ones, right? Just because it's fiber channel doesn't mean that it's capable of doing NVMe OF, right?
It's real close. The crucial thing to understand about NVMe OF is the data traffic looks like FCP. It looks like SCSI.
Yep.
The upgrades of SAN switches in the middle would be a small firmware upgrade so that something like the name server and the management software for it understands the magic protocol number that's used for NVMe OF.
So I understand currently SUSE Linux is the only one that has NVMe drivers even in its stack or qualified. Is that right?
Natively, yeah. For native support, that's correct.
Well, that's what I did when NetApp launched with OF. They were basically saying it's one version of Brocade with one version of SUSE for now.
Yep.
Yeah, it's probably worth something pointing out, right?
So, Rich, the only other note that I made during this is in the slide that talks about all the places we already have it, right? And it highlights the PowerEdge servers and the VMAX and the data domain and all those things. And it says, and I think you mentioned coming soon to you in the mid-range. I'm on the other session that is covering. I forget what it's called now. It used to be called .next, but it's called the Future Storage or something now. There's literally 2 slides that's going to discuss this, and it will come out in full detail. But just for the presenters of this deck, so you guys know, that session will talk about all those things, but we don't want to oversell what they are going to talk about. They are going to talk about the NVMe hardware, the Unity 5.0 release, but they are not going to talk about actually our next platform That was a decision that it came from the product BU. So at least on the slides, they may talk about it off track. So I would say on this slide, we focus very heavily on our entire portfolio is NVMe based today, guys, besides like some mid-tier storage. Like, no big deal. And by the way, our mid-tier storage still owns 35% of the market share. You know what I mean? Like, I wouldn't oversell how much they're going to learn in a session they haven't been to yet. They will hear about what our future roadmap is as far as NVMe in the mid-range, and I think I just leave it at that. It's probably
Paul, what
nuanced,
slide
but
number was that? That was in regards to the midrange.next slide?
It's the one up, 35.
Yeah. Okay, I took a note on that as well. I remember we had dialogue on it.
37 should probably go all together.
Yeah, 37, because you have the whole Unity Bolero thing, and then if somebody reads this in a vacuum, does that mean that the next thing we'll have with NVMe, we have to wait for midrange.next? Well, that really doesn't do the Unity Bolero story any justice and that stuff, so that's all I was going to say.
Yeah,
more to come, whatever, you know.
I totally agree. I think what we should do is maybe kill 37 and in 35 say, for you guys that have not been to the Future of Storage session, or for the ones that have been, however you want to, present that. If it's the, obviously if it's the first delivery of this, none of the people in your room will have been. You will learn all about what our plans are as far as adding NVMe into our mid-range, and it's a very healthy roadmap. Stand and leave that to Caitlin and people to handle in a different session.
So Rogoff and I were presenting this deck to some of the folks in the COC, the FMMs, and I know we had dialogue on it, one of our dry runs, and we took out the 2019 and made the other bubbles say today and all that. One of the guys says, wait a minute, PowerEdge was out before PowerMax. Why is that to the right of it?
But it wasn't. It was 6 months. It was 6 months earlier.
That's what I'm saying. So PowerEdge should be to the left of PowerMax, yeah.
No, I think the reason it was on there like that is because we in Sim V3 we were using it about 6 months before PowerEdge, and so even though it's called PowerMax today,
okay, all right,
we kind of put it to the left, but totally nuanced. I know it doesn't matter.
But that was my point last time, is that people are going to interpret whenever you see a chronological thing with bubbles of dates, they think roadmap, right?
Yeah.
So how about this?
So fair enough, guys. No, I think you can say mid-range.next, but I just would leave the weight to Travis and Caitlin or whoever's going to be in that other session, because there's been a lot of discussion about very specifically what we're going to say and what we're not. There's been a lot of discussion.
Well, as you always know, my argument's always for transparency, because they're SEs, and if you don't tell them, they're going to make shit up. That's the bottom line. Whatever you don't tell them, they're going to assume we're not doing. That's the bottom line.
Yes. So they're going to hear it. They just don't need to hear it from us in this session. Let them hear it in a different session.
I want it, brother. Okay. So leave midrange.next. I pulled 37.
Okay.
Find out what they're going to say in the courses, yeah.
So anyway. Okay, cool, man. That's perfectly fine. I mean, because that slide was pretty much an empty slide anyway. It was just going to be me pointing at the screen going, hey, there's more stuff coming, but I don't want to emphasize it if they're not going to emphasize it as well.
Right. I took some notes. You just passed one of the slides I saw, and I know you got it from probably Vince or somebody that was a champ. It looks like it was one of the champ decks. So when we show the active scale, so 43 would be 41 is one of the build slides, as well as 43. It has to do with what controllers are control which drives in the DAE, and I believe, but. Yep. Somebody's going to say, why are 25% of them green and the other 75% blue?
Yeah, that's a great question.
So I just want to throw that out. Does that mean that the little red X that died? I don't think that's what it means, but.
No, the plan is that those little green ones are going to be SCM and the blue are going to be NVMe. And that's why it's all blue on the other side.
There we go.
I mean, one of the things, and I probably didn't state this very well because I'm probably talking too fast, is that one of our huge advantages going into this next media transition is that we have fast tiering already under our belt. We know how it works, right? Because SCM, when we first release it, we're not going to sell entire arrays full of SCMs probably because it's going to be too expensive. That's going to look exactly like the flash transition, right? So I can see us using these really fast new devices as a tier, and we're really good at that. Whereas Pure, do they have any experience with tiering at all?
No.
Right. Does NetApp has some experience, right? But it's literally they have read caching, and they're really good at read caching, and that's it. That's what they got. That's what their whole flash cache, PAM modules, all that crap was read tiering is all. I mean, read caching is all it really was, and a place to line up your writes for you drop them on a disk. So we have a huge advantage because of fast tiering.
Hey,
And
Rich.
Yes, sir.
You did talk about that, by the way, and I think it's super important.
Okay.
Another talk track that you could add to this, and I heard Vince on the phone. If you're still on, keep me honest here, Vince. What we are seeing so far from an NVMe OF perspective, okay, can I reduce the latency in the fabric between the host and the array? That when customers take that on, they're getting somewhere, I'll call it in a 50 microsecond gain, okay? And just ish, okay? The way that we manage data with our machine learning algorithms inside of the PowerMax is we don't compress the hottest 10% of the data. So we effectively are reducing the decompressed time that everybody on the market is actually taking on this already. So we would argue that our PowerMax is just as fast without the NVMe OF capabilities from a latency perspective as our competitors are with these platforms because they have to take that penalty. Does that make sense?
Love that
That
you
makes
got that
perfect sense.
exactly that way, Paul. Awesome.
How do we state that, though, and where do you think we should state it? Make it the talk track?
I just think when you're talking about NVMe OF and that you're saying, hey, you know, there's some competitors out there that are already adding this, not only is it flawed, which we've clearly defined for you, right, and complicated and is not going to be as easy as they say, we don't even need it today. And we're still, because we're still faster. Like the whole point of NVMe OF is to take more latency out of the whack-a-mole story. And we don't even have to. We're already doing it because we're so advanced in this machine learning capability in the PowerMax.
Maybe we just state that as part of this. Oh, here. And Mark Rogov redid this slide deck and read all these slides. He did a great job, man. Like here, remember when the VMAX drives by? I'm trying to find the slide. It's all animated. It's hard to tell. When the VMAX drives through on this slide here, maybe that's when we mentioned that.
Yeah. So Vince, I think I heard you speak up. Am I too far off base there, or are we good? Can we drive a stake there?
No, I think that's accurate. I think it's the 10%. We call it RHD, right? Red Hot Data. So the busiest 10%, we don't squeeze it because chances are we're going to have to go unsqueeze it.
Does it make sense to does it make sense to put it in the slide where you're comparing between the two solutions and talk about machine learning, just to put it in the talk track there?
No, I don't think so.
Yep. Also, be careful about the messaging. I understand where this is going, but I heard somebody very quickly spin it as we don't need NVMe OF. We're headed there, so don't leave the impression that it's not. It's rather, look, we're already better. These guys need that to catch up to us. We're going to do it as well, and we'll be ahead again.
How about this? Because we don't compress the hottest 10% of our data on PowerMax. Oops. We'll find a place to put it into the talk track for now. Because we don't compress the hottest 10% of our data on PowerMax, we already get a 50 microsecond decrease in latency, which is about the same as the gain given by NVMe OF. So
Perfecto. Yep.
we get that now. When we get NVMe OF also, we'll get another 50 microseconds.
Bingo. That's where to go.
Got it. Okay. And we'll talk about that in this slide because remember the VMAX driving through and we talk about the storage controller decreasing latency? We can talk about it here. That actually makes sense on this slide.
Could you take a look at slide 17? I took a note on it. On the x-axis where you have them labeled, could we somehow, like to the left of HDD in the bottom row plus SAS, put storage medium and then interconnect or something like that?
That's a good idea. So
or make them different colors too. Like since they're all white, I don't know. Like yeah.
I'm with you.
However you want to do it.
No, that can make sense because it does bring out the fact that it's a media transition and this is an easy, quick thing to do. Hang on.
And that SCM box is in like a lime green color, which happens to be the same lime green as software latency. Is there any correlation there, or it's just?
No, it's just the first color on the thing when I picked it. Hang on, I'll make it blue. It actually matches better anyway. Oops. And we'll do it in blue. So it just matches anyway.
Yeah, I meant the word to the right, the one that reads storage class memory technology. That one is in green.
This is supposed to. Yeah, that's on purpose because honestly, that's the big benefit, right? The benefit storage class memory and NVMe. NVMe by itself.
Yeah, I get that, but my point was is it's the same color as the software latency in the key, and I wasn't sure if.
I get it. No, I get what you're saying. Okay, I'll just make it blue.
And software latency, I mean, is software a very ambiguous general term in this sense? You're talking about the code on the drives, I assume?
Hang on one second. I'm doing my pitiful version of multitasking that only I can do. Software latency is the client latency. The latency of the client.
Oh, okay. All right.
It's IO stack. It's IO stack in the client.
Got you. And on this slide, as well as 3 or 4 other ones, our footers are fighting for the bottom down there.
I wonder why that is. Let me go dig into.
Because one is from a template.
That's not a footer. That's just a. They're done. Because we got this from NVMe Express people. Actually, let me not do that because I need to give attribution.
Yeah, just put on the right. So slides 17, 18, and 24 all had it that I saw.
Yeah. You are a very observant man.
I'm good at pointing out problems to other people's work.
So,
you must be a manager.
I'm married. I'm married.
Oh, you're married? Got it.
Just check in on time. We got about 5 minutes left, and I want to make sure we're comfortable with presenter teams and logistics. So, want to make sure we're highlighting other things that are critical to the deck. Are there any other things that people want to bring up while we have a chance to discuss as a team?
So, Stephen, you mentioned a bunch of things there. So, as far as presenter teams go, I believe it's me and Mark. Mark, are you you said that? I mean, it's me and Chris. Mark, are you going to be able to make that first day? If not, maybe you want to swap over to my team.
Mark's in an ops review, I believe. So he's not flying in till Tuesday morning, and I think he lands like 9:30. So I told him I'd get in Monday and I would take his shifts.
Okay. Well, there's on Monday we have a simultaneous. We're both going at the same time at 8:35. I believe it was Monday. One of the days I thought
that's
Monday,
the last day. That's Wednesday.
So on Monday we don't have any conflict.
There's no sessions on Monday, Rich. They're
I mean,
all mandatory bigger sessions.
Tuesday morning.
Tuesday, Wednesday.
Tuesday morning.
Yeah,
I'm sorry.
Yeah.
The only sessions on Wednesday are running concurrently from 8 a.m. to 9:30, and both Mark and I will be there. He and his, and me and mine.
All right. Stephen, is that? Do you have the latest grid pulled down? Is that true? I want to say there is a concurrent one Tuesday morning. Do we just...
I thought there was.
Okay. Have one as of yesterday. Let me pull it up real quick, guys.
Hey, I'm gonna upload the latest deck for everybody, guys. I think we're gonna put a stamp on this one and call the deck itself done.
Rich, one of the notes I took had to do with that silly font that we have in our thing, that Roboto stuff. But yours came out right on slide 47. Did you change that?
Slide 47.
Okay, there is a duplicate session on Tuesday, but it's not until 3:45 p.m. So
right.
Mark should be there by then.
Yeah.
Yep. In the morning,
you're all set. When I watch Roboto, weird, dude.
So what I'm just going to let people know, what I'm going to do is I'm going to send out an email. I'm going to ask everyone for their mobile phone number and their arrival and departure time. I am going to ask for a volunteer from this team to support an end of day Wednesday future proof session. So whether that's because Chris Shoebridge has to cover other team meetings and has to leave, and that the future proof has an end of day Wednesday session. So if
I don't know what happened.
I'm happy to do that.
Assuming we don't have a conflict. If it's Vince, I'm glad to do it too. I'm there. I've got a red eye out Wednesday night, so I got plenty of time.
Okay. So I got two. I think what I'll do is I'll just I'll tap someone. I think Vince. The only question for me is because you also have the what's next, right? So and I just want to make sure
Haven't
you.
looked at all the timing yet.
Yeah. So you the one that we're looking to cover is this. I believe this 4:15. So. So I think you're spoken for there as well.
Hey, Steven, I don't fly out until Thursday morning, so I might be able to help you out with that.
Okay.
You're to be great at this too.
You're a winner. And anyone else who wants to is happy to track me down, and we can jam that room full of people to support. But that basically is it for me. I will send that email out for just this session. For making sure that we know when people are in and out. And I think that's it. So any other questions? Was there any more? And apologies. Was there any more of the deck to go through?
There was literally two. There were 3 slides left. Let me throw them up really quickly, but I don't think they're really critical to this. There's a wrap-up QA. Here, do it. Let me display them really quick. We wrap up by saying, hey, do you understand what you did? Right? So this are the 3 things we're trying to accomplish. Do you feel like we accomplished these things? Ready, are you? We thought that was funny. Give credits where credit's due to people who helped out. Data we got, information we pulled. Basically, if we stole your material, you should be on the slide. Then we have QA questions.
Yeah. Presentation's not coming through Skype.
Yeah, Rich,
that
we can't
again?
see anything. We can't see anything, Rich. It's not displaying, but I think we're okay with that. Hey, a quick shout out to everybody before we get off. I want to sincerely thank every single person that has been on this call, and to Rich and team and Mark and Chris and Mark for all of the hard work putting this together. It's been a big effort and a group effort, and we sincerely appreciate to everyone on the phone all the hard work and effort and support to make this a success. So just sincere thank you.
Yeah, I agree, Paul. Thanks for saying that. I think Rich has done. Everybody's done a tremendous job. Rich has really done above and beyond on this. So thanks, Rich, for your leadership here.
Welcome, man. It's been fun. I'm looking forward to presenting it. We need to decide on our teams, like our flow. Like Chris, you and I need to sit down and chat about who's doing what.
Yeah, yep. I was just going to ask that.
Yep. So maybe you and I can take it offline because each team can do it their own way.
Sure.
Because I'm gonna have Kurt do a couple small things too, but you and I can discuss that out of band, okay?
And I don't have a copy of that presenter grid, but are we going to? It'd be good if we could keep Johnny Carson and Ed McMahon together,
Yeah.
Johnny Carson, Ed McMahon.
I will send out when I send the request for your flight time stuff. I will send out the presenter grid.
And the deck, you're going to send the deck. I still can't get to that
Yep.
SharePoint. So
I will send it right now. I'm calling it done. I'm saving it. We're done.
it's done.
I fixed all those footers.
Beautiful. Bravo.
All right, folks.
All right, guys.
Chris, I'll set up a call with you later this week with you, me, and Chris, and we'll chat. You, me, and Kurt, and we'll chat about how we do it. Mark, you're going to want to set up a call with Mark. The Marks are going to have to talk, and you guys get y'all's presentation.